Einstein's relativistic theory of gravitation, general relativity, will shortly be a century old. At its core is one of the most beautiful and revolutionary concepts of modern science, the idea that gravity is the geometry of four-dimensional curved spacetime. General relativity has been accurately tested in the solar system. It underlies our understanding of the universe on the largest distance scales and is central to the explanation of such frontier astrophysical phenomena as gravitational collapse, black holes, X-ray sources, neutron stars, active galactic nuclei, gravitational waves, and the Big Bang. Gravity is one of the four fundamental interactions. The origins of general relativity can be traced to the conceptual revolution that followed Einstein's introduction of special relativity in 1905. Newton's centuries-old gravitational force law is inconsistent with special relativity. According to Newton's law, two bodies of mass m1 and m2 attract one another with a gravitational force whose magnitude is F, which is equal to the gravitational constant times the first mass times the second mass divided by the radius between them, squared. Newtonian gravitational force acts instantaneously. The force on one mass depends on the position of the second at the same time. However, instantaneous interaction is prohibited in special relativity, where no signal can travel faster than the speed of light. Take the Earth orbiting the Sun, for example. If the Sun were suddenly to disappear, what would happen to the Earth? Light takes about 8 minutes to travel from the Sun to the Earth. What would the Earth orbit around for 8 minutes if the Sun were gone? Newtonian gravity can therefore only be an approximation to a yet more fundamental theory. Einstein saw that the experimental fact that all bodies fall with the same acceleration in a gravitational field led naturally to an understanding of gravity in terms of the curvature of the four-dimensional union of space and time, spacetime. Mass curves spacetime in its vicinity, and the trajectories along which all masses fall are the straight paths in this curved spacetime. In Newtonian theory, the Sun exerts a gravitational force on the Earth, and the Earth moves around the Sun in response to that force. In general relativity, the mass of the Sun curves the surrounding spacetime, and the Earth moves on a straight path in that curved spacetime. Gravity is geometry. It is an experimental fact that all bodies fall with the same acceleration in a uniform gravitational field, independently of their composition. If Galileo could have dropped a cannonball and a feather from the Leaning Tower of Pisa in a vacuum, they both would have accelerated towards the ground at 980 centimeters per second squared. This equality of accelerations is one of the most accurately tested facts in physics. Take, for example, a ball thrown upwards. The ball starts with some initial velocity, decelerates, reaches a maximum height, accelerates downward, and returns to the surface of the Earth. Any other body thrown upward from the same initial position with the same initial velocity would follow exactly the same curve. The uniqueness of trajectory in space and time is a special property of gravity. The motion of a body in a magnetic field depends on what kind of charge it has. Bodies with one sign of charge will be deflected one way, bodies with the opposite charge will be deflected the other, and bodies with no charge will not be deflected at all. Only in a gravitational field do all bodies with the same initial conditions follow the same curve in space and time. Einstein's idea was that this uniqueness of path in space-time could be explained in terms of the geometry of the four-dimensional union of space and time called spacetime. Specifically, he proposed that the presence of a mass, such as the Earth, curves the geometry of spacetime nearby, and that, in the absence of any other forces, all bodies move on straight paths in this curved spacetime. Bodies free from forces move on straight lines of the three-dimensional Euclidean space in Newtonian mechanics. That's part of Newton's first law. Einstein's idea is that the Earth moves in its orbit around the Sun, not because a force of gravity acts on it, but because it is following